Hello, and welcome back to the course on quantum mechanics. We are still on the fifth chapter of this course. So let's first review some of the concepts that we have discussed in the previous lessons. So in the previous lesson, we have discussed about identical particles. So the wave function for a two-particle system is given by this equation, wherein we take into account all the possible combinations of the states of the identical particles. So the plus operation corresponds to bosons, identical bosons, and the minus operation corresponds to identical fermions. So the Hamiltonian for a two-particle system is given by the total kinetic energy plus the potential energy of the system. So in this lesson, we will be progressing into many particle systems and end up with a solid. So we will be basically discussing the quantum theory of solids. So let's start with atoms. So atoms basically have Z number of protons and Z number of electrons. So the Hamiltonian now of an atom is basically the kinetic energy of all the electrons and the potential energy between the electron and the electrons and the protons. So there's a summation because there are a lot of electrons and protons. There's Z number of protons, Z number of electrons. Plus, you have the interaction. So this is just the potential energy between the proton and the electron, and you also have the interaction potential energy between the electrons themselves. So their interaction is actually repulsive. The interaction potential energy between the proton and the electron is attractive. So the 1/2 factor here is to take into account double counting. So in this case, the Hamiltonian, the time-independent Schrödinger equation still holds, and the wave function of the system is actually anti-symmetric because our particles are fermions. Proton and electrons are fermions. So if you now have many atoms, so you now create a solid. So in a material, such as a solid, there's actually what we call valence electrons. This is the outermost electrons, or the electrons in the outermost shell, or the electrons in the outermost orbital. And these electrons, these valence electrons, can actually be detached from an atom, and they can roam around the volume of the material. So this means that they are no longer subject to the Coulomb potential energy of a specific atom, but now to the combined potential of all the atoms of the material. So there are two theories for quantum theories for solid. The first one is the Sommerfeld free electron gas theory, wherein you treat the electrons as, or the solid as, free electrons in a box, and you ignore all of the forces except at the boundaries. So basically, it's a electrons in a three-dimensional infinite square well potential. So one advantage of this theory is that you can calculate the Fermi energy. I will explain the Fermi energy later. Another theory is the Bloch theory, wherein you take into account the potential of each of the atoms. So the electrons experience periodic potential due to the regularly spaced nucleus of the atom. So the atoms can be trapped, it can be free again, it can be trapped, it can be free again. So there's a periodic potential. Now, one advantage of Bloch theory is that you can calculate the energy band structure and the band gaps of the solid. So none of this theory is entirely correct. So these two theories actually complement each other. They describe the whole picture of the quantum theory of solids. So let's first start with the free electron gas theory. So basically, they can be described as free electrons inside a box. So in this theory, electrons are free inside the box. So they experience no force inside the box except at the boundary where the potential energy is infinite. So it's basically particles in a three-dimensional infinite cubical well, or particle in a box for simplicity. So the wave function is just the three-dimensional version of a particle trapped in a one-dimensional square well potential. So the width of the well, or the width of the box, are now Lx, Ly, and Lz. And the energy level is given by this one. So you have n squared pi squared h bar squared over 2ml squared. So you have x, y, and z components. Of course, they're just equal to the kinetic energy of the gas, h bar squared k squared over 2m. Where k squared, it has three components. It has an x component, a y component, and a z component. So in this theory, we have, when we work in the k space or the reciprocal space, take note, this is the k space or the reciprocal space. K is the wave number, 2 pi over lambda. So it has a unit of 1 over length. So that's why it's called reciprocal space. So you have kx, ky, and kz. So this is the reciprocal space or the k space. So in k space, you have what we call a Fermi surface. So the Fermi surface is the boundary separating the occupied states and the unoccupied states. So the occupied states are the bound states, the unoccupied states are the free states. And the Fermi energy is just the energy of the highest occupied state. So the Fermi energy from the free electron gas theory is just h bar squared kf squared. So kf is the Fermi wave number, and it's equivalent to 3 rho pi squared to the 1/3, where rho is what we call the free electron valence electron density, which is just equal to the free electron density, because only the valence electrons can become free electrons. So Q here is the number of valence electrons per atom, and it's usually 1 or 2. There are only 1 or 2 valence electrons per atom. N is the total number of atoms, and V is the volume. So basically, you will have a number density, number per unit volume. So when the electron is bound, this means that its energy is below the Fermi energy. And when its energy is above the Fermi energy, then it becomes a free electron. So the total energy of the free electron gas in this theory is given by this equation. So it depends only on the mass of the electrons and the Fermi wave number. Now, if you try to calculate the change in energy of the gas whenever the gas expands or contracts, so if you take the derivative of that with respect to the differential of that, then you will get this one. So we will focus only on the relationship between dV and dE. So this means that if the box expands such that dV is greater than 0, then dE is negative. And the converse is when the box contracts, so dV is negative, so you have negative sign here, dE is positive. So when the size of the solid expands, the energy actually decreases. So the free electron gas actually releases energy when the volume expands and absorbs energy when the volume contracts. So if you try now to find the differential work done on the gas, this is the different change in energy of the gas. And if you try to find the differential work done on the gas, so it's just the negative change in energy of the gas. And it's equal to PdV. P is the pressure, then dV. So from this, you can see that there is a pressure in the free electron gas, and it depends on the free electron density. The higher the free electron density, the higher the pressure. So usually we call this quantum pressure or degeneracy pressure. So this is the stabilizing internal pressure for solids. And this is the reason why solids don't collapse or don't contract. Take note that if you have a gas can collapse into a liquid, and a liquid can contract or collapse into a solid. But if you have a solid, it can no longer further contract because of this stabilizing internal pressure given by this equation. So it's a quantum effect. It's not dependent on thermodynamic effect. It's a quantum effect. Okay. So let's now go to the Bloch theory. So basically, you are describing an electron in periodic potential. So this is the atom, the first atom, second atom, and the lattice is actually periodic. So this is the last atom or the nth atom. N is the number of atoms. So the lattice is actually periodic. So you have which means you have a periodic potential. So you might be thinking, why am I using a barrier, a delta function barrier? Actually, if you like, you can actually flip this one and instead have delta function wells if you like, but the analogy is just the same. So the wave function is not periodic, even though the potential is periodic, the potential energy is periodic, but the wave function is not periodic. So this is the wave function of the nth atom, or the nth location, x plus Na. And we usually call this the Bloch theory, where k here is just a number. It's 2 pi n over Na. N, again, capital N is the total number of atoms. N is just an integer here. So don't be confused with the two n's. So solving for the wave function by applying the boundary conditions, you can't actually explicitly solve for the wave function because you will be stuck in a transcendental equation. But from the transcendental equation, you can actually get the energy spectrum. Because take note, this transcendental equation will solve for values of k. And k is related to the energy. So if you know k, you know the allowed values of k, then you get the allowed values of energy. So hence, you can describe the energy spectrum or the energy band structure for this periodic potential. So this is actually the plot of the left-hand side of our transcendental equation, or sorry, the right-hand side of our transcendental equation, cosine Ka plus m alpha over h bar k sine Ka. So it looks like a damp oscillation. Now, from the left-hand side of the our transcendental equation is actually a cosine function, cosine capital Ka, and the value of cosine is actually just from -1 to +1, meaning this is the only region that's allowed. So if we zoom in that region from -1 to +1, then these are just the allowed values of Ka, and hence if you get the allowed values of Ka or K, you get the allowed values of energy, and these gaps here are actually the disallowed values of Ka. So the collection of all the values of K from this part to this part and from this part, that part, they actually form an energy band because there are several values of K there. So that's the energy band. And the disallowed region, the disallowed values of Ka, which means the disallowed values of energy, corresponds to the energy band gap. So no energy here, no states here. So if we rotate this one such that we are now the y-axis is now our energy, then our band structure will look like this one. So the valence band is the highest field band. It contains the valence electrons, and when valence electrons become conduction electrons, they actually become free. They are now free to roam the solid. Now, if you have insulators, the gap between the valence band and the conduction band is the lowest unfilled band. It's actually very large. That is why in insulators are not good for conducting electrons, say conducting electricity, because there's a band gap here. The valence electron can cannot essentially become free electrons. If you have a semiconductor, then the band gap is just small enough such that the valence electron can go to the conduction band, depending on what you did with the semiconductor. And if you have a conductor such as metals, then there's actually no gap between the valence band and the conduction band. So essentially, all of the valence electrons are conduction electrons, and essentially they are all free electrons. Okay. So first example. So for the ideal free electron gas, what is the average energy per free electron? Write your answer in terms of the total, or in terms of the Fermi energy. Okay. So this is the Fermi energy. And in terms of the free electron density, NQ over V, so this one. And if you want to try to find the average energy of the free electron gas per free electron, so basically you divide the total free electron gas energy divided by the number of free electrons. So in order to do this, we need to write the total energy of the free electron gas in terms of the Fermi energy. And in terms of the Fermi energy, it's actually 3 NQ, and it's just a number, the number of atoms. Q is just the number of free electrons or valence electrons per atom, which is usually 1 or 2 over 5 EF. So the average energy is just the total energy over the total number of free electrons, which is N times Q. So divide this with NQ and you will have 3/5 the Fermi energy. So the average energy per free electron is actually 3/5 of the Fermi energy. So this next example is about copper. So you are given the density of copper, 8.96 grams per centimeter cube. You're given its molar mass, 63.5 grams per mole. And the first question is, what is the Fermi energy for copper? So we use the Fermi energy formula. But before we can use the Fermi energy formula, we need first to know the number density, free electron density, rho. So it's just the number of N. It's supposedly NQ over V, but we will assume that Q is equal to 1. There's one valence electron per atom, so it's just N over V. So N is the number of atoms. How do you find the number of atoms in your copper? So you multiply the Avogadro's number by the mass of the copper divided by the molar mass. Okay, now you will obtain a term mass over volume, and mass over volume is the quantity called the density. Mass over volume density, which is given 8.96 grams per centimeter cube. So we can now solve for the free electron density. It's just Avogadro's number divided by the molar mass times the density of copper. So we use this one. We substitute it in the Fermi energy formula for rho, that one. And Avogadro's number is just 6.02 times 10 to the 23 atoms per mole. You convert to standard units. You look for the values of H bar. M is just the mass of the electron. We're given the molar mass, the density. So if you use standard units, you will get a value of joules, and you just convert that into electron volts. So usually in the quantum realm, since the values of energies are very, very small, we use the unit of energy called electron volt. 1 electron volt is 1.602 times 10 to the negative 19 coulombs, negative 19 joules. Okay. So for letter B, what is the velocity of the electrons? Is it non-relativistic? So assuming that the Fermi energy, the energy of the highest filled band, is equal to the kinetic energy of the electrons in copper, then EF is 1/2 mv squared, and you can solve for the velocity, and you will get a value. So I have already converted the value in terms of c, the speed of light. So it's 0.00525 c. So it's very, very small as compared to the speed of light, meaning it's a non-relativistic speed. So you don't need to use the theory of relativity here. So for the third question, letter C, at what temperature would the characteristic thermal energy, which is kT, Kb is the Boltzmann's constant, and T is the temperature, equal to the Fermi energy. So you just equate the Fermi energy by kT, and you will get the characteristic temperature of 8.17 times 10 to the 4 Kelvin. So the temperature is in Kelvin. The SI unit for temperature is Kelvin, the absolute temperature. So for letter D, what is the quantum pressure, quantum or degeneracy pressure of copper based on the gas model? So use the formula for P, where we obtained rho, the free electron density, as NAD over M, Avogadro's number, molar mass, density, and you will get 3.84 times 10 to the 10 Pascal. So this is actually a very large pressure. If you will recall, 180 m or 1 atmospheric pressure is just times 10 to the 5. So this is 10,000 times stronger than atmospheric pressure. So the atmospheric pressure cannot crush basically a solid, cannot compress a solid, because the internal stabilizing pressure is 10,000 times stronger than the atmospheric pressure. Okay. For this example, we are asked to find the energy level of the top of the second energy band for these values. We're given m alpha A over h bar squared is 10, and alpha over A is 1 electron volt. So the top of the second energy band. So this is the second energy band. This is the bottom of the second energy band. This is the top of the second energy band. You will notice that the top of the second energy band lies around 2 pi. 6.28 is actually 2 pi. 3.14, this is pi. 9.42, that's approximately 3 pi. So Ka here, for the top of the energy band, Ka is actually approximately 6.28 or 2 pi. So that's the value of our Ka. Meaning K is actually equal to 2 pi over A. And since h bar squared over m, from our given, which is m alpha over A over h bar squared is 10, meaning h bar squared over m is alpha A over 10. So we now proceed to evaluating the energy, h bar squared k squared over 2m, and it's approximately that one. So k is approximately 2 pi over A squared, and h bar squared over m from our given is alpha A over 10. Okay. And since alpha over A is 1 electron volt, then we get approximately the energy corresponding to the top of the second energy band is 1.97 electron volt. So that is the top of the second energy band. This is the first energy band, second energy band. The top is this one. You can actually calculate also the bottom of the second energy band, provided you are given the exact value, or we can interpolate the exact value of K. Okay. And that is it for this lesson. So it's basically a crash course of solid state physics. Take note that the background or the foundation of solid state physics is quantum mechanics. So that's basically a crash course of solid state physics. So for our next lesson, we will be talking about another realm of physics, which is statistical mechanics, and we will introduce the quantum version of that, which is the quantum statistical mechanics. So I will see you again in the next lesson.